Okay. All right. So good morning, everyone. Sorry for the delay, the network delay. Actually, we had serious issues setting up, but I'm glad we're able to continue. All right. So if you can hear me, I don't know, since I'm not physically present in the hall, if you can hear me, you can just do a thumbs up on the YouTube channel, and I will be able to see. Okay. So can you hear me? Hello, can you hear me? Okay, cool. All right. So last week we were talking about training a neural network. Okay, and specifically we are doing it in PyTorch. This guy here. All right, and the purpose of this lecture is to give you some kind of intuition as to what happens in the background when you train this network. Okay, so that you don't fall into some known pitfalls like you training a network and it's never giving you the right results. Okay, so this is what we did last week, although we were not able to complete this note. So I'll just run through to the point where we stopped. Okay, so we are looking at classification problem, all right? And specifically, I said that classification problem comes in different variants, okay? The most simplest one is the binary classification, where you want to predict whether an instance or a sample belongs to one class or the other class. So in this case, there are two possibilities, either one class or the other class. So we call that a binary classification problem, okay? In a situation where you have more than one classes, okay, more than two classes, sorry, then we call it a multi-classification problem or multi-class classification, okay? So that could be maybe you have an image that you want to detect or predict whether that image contains a dog or a cat, okay, or a sheep, and so on and so forth. Those are multi-classification problems. So, by the way, the note credits is actually from Mr. D Book. Okay, he has so these notes were actually retrieved from his GitHub repository. You can always check it out and get more information. Okay, so typically in a neural network or in a machine learning project, what you do is you collect data, okay, and you turn the data into a tensor, all right, and then you either build your own model or you pick something called the pre-trained model. We'll talk about it in a moment, okay. Once you decide what model you want to use, okay, either by building it or maybe getting it pre-trained, then you can now fit the data that you've collected to that model, okay. So you feed the data to the model, and with that, you can start making predictions. Okay. Well, the next thing you might want to do is to evaluate the model, whether the model is actually doing the right thing, whether the model is making the right prediction or not. Okay. And if you want to maybe have the model live, then from time to time you can schedule some retraining, to improve the model. Okay. You can also save the model and reload it whenever you need it. So this is a typical workflow for machine learning projects. So in this notebook, there are different topics that are covered. Okay. There is the architecture of the neural network. Remember, I said the neural network is just a bunch of a series of function compositions, okay, where you do several matrix multiplication. You pass it through some linearity and then you multiply it to another matrix into another linearity and so on and so forth. That forms the architecture of your neural network, okay. So in this note, we looked at some architecture. We looked at binary classification problem. Looked at building the model using PyTorch, okay, specifically for classification model. We look at fitting the data, okay, making prediction and evaluating the model, okay. We also explore some issues concerning nonlinearity, and then at the end, we put everything together to make a multi-classification task, okay. If you have any questions, you can post it live on the YouTube channel, or you can also post your questions live on the Telegram channel. I'll be able to see it and respond accordingly. Okay, so just give me a moment. Okay, so that will be Biz Artificial Intelligence channel. If you have any questions there, you can just post it. Okay. So a typical neural network contains the following. It contains an input layer, okay? It contains several hidden layers, okay? And these hidden layers contains neurons, okay? And then it contains an output layer. It also contains something called activation functions, okay? And you also have the loss function and an optimizer. So let me briefly explain some of these things. So let's say you have some architecture where you have you've defined some matrix that multiply the inputs, okay, and another matrix multiplying that other input, and so on and so forth. So you have this architecture. How do you then train the model? The idea behind this is, if you have a matrix, if you have these, you have defined this architecture. Initially, the matrix, those matrices will contain random variables, okay? So it is now the task of the training process to fine-tune those variables so as to match the particular target that you want for the neural network. And to do that, you define something called the loss function. So what the loss function does is to say, okay, given a particular prediction, okay, and given what you know about that input, how well does the prediction match the output? So typical loss function values will range between 0 and some large number, okay? So if what your model is predicting and what you know as the right answer is 0, it means, your model has converged. There is no loss, okay? If the difference between what you know and what the model is predicting is some high value, then you have to go back and change the weights in the neural network, okay? And the technique for doing that is the optimizer, okay? In fact, specifically, one of the techniques for doing that is something called stochastic gradient descent, which we are going to see in a moment. All right, so that's that. So in this notebook, okay, I see somebody is asking if there's an avenue for discussion. So you can always do a chat on, always do a chat on the Telegram page under artificial intelligence, and I should be able to see it immediately. Okay. So remember I said at the beginning, you prepare your data. So fortunately for us, there are some data sets that are available for us to play around with, okay? One of that data sets is the mixed cycle data set. It's a synthetic data set where I can, ask it to generate certain samples, okay? And these samples, if you look at the trend of the data or the manifold of that data, it follows a cycle, okay? So here we specify that we want 1,000 samples, okay? And then we specify the amount of noise we want for the cycles, and then the random state. So if you run this, you're going to generate the X data and the Y data, okay? The next code basically just looks at these data. So the X data, they are two-dimensional data, okay, as you can see. So each sample has two values, okay? And the Y data are just real numbers, okay? Specifically, these are integers, really, okay? So 1 indicates that the cycle belongs to a particular class, and 0 indicates that the cycle belongs to the other class. So this is a binary classification problem. Okay. All right. So we can prepare them in a data frame, and this is what you get. Okay. So where here we just put the features. Okay. So this is the X1 feature, and this is the X2 feature followed by the label. And what you now have is a data frame where you have the two features and the label. Okay. So what we want trying to do is we want to get a model to be able to get these input features and be able to predict this label at the end of the day. Okay. All right. So one other thing that we might want to do is to look at how balanced the class labels are with respect to the data. So this code is just to give us a value count between the labels. So as it stands now, there are 500 samples with 1, labeled as 1, and there are also 500 samples labeled as 0. And we can plot this and see the data set. So this is how the data set looks like. Okay. Obviously, these are two classes. The first class belongs to these points, the inner circle, okay, denoted as blue. Okay. The second class belongs to these red points, denoted as red. So we want to build a neural network to be able to do this classification. That is, given an input, we want it to be able to tell whether the point is either a blue point or a red point. So this is essentially a classification problem. Now, if you notice, all the points do not perfectly follow the cycle. Okay, this is because we specify a noise ratio of, if you go back to the beginning, 0.3. So if I remove this noise ratio, 0.0 noise, then I'm going to get, a perfect cycle, which is this guy here. But this is not what I want really, okay? Because the data you get in real life will be noisy. So you want to be able to train a model with the inherent noise. So the model should be able to, sieve out some of these irregularities automatically by itself. So this is why the data set that we have, okay, introduces some kind of noise to simulate the noisy process of data that you have in the real life. Okay, if the noise is very, very high, then of course you probably will not even be able to make proper sense of the data. Okay, so this is a noise of 0.7, and this is the data where we have. It doesn't even look like a cycle anymore. So we expect that we assume that in real life, we're going to have maybe some noise, but it's not going to be so much. So this is a noise of 0.3. It's still not looking like a circle, but what we had initially was 0.03, very low white noise. Okay, so this is what we had. Any questions? Okay. All right, so if we have this data, remember I said we want to build a model that will be able to classify whether each of given any points, whether the point is a blue point or a red point. Okay. So we can build a simple model to do that. All right. For a start, we need to divide this data into the ones we want to use to train the model and the ones we want to use to test whether the model is getting it correctly. Okay. So let's really do it. Let's just look at that in a moment. So the first thing here is, what is the shape of this data? I think we've seen this in previous classes. So we have 1,000 data points. These are the X values. Each of the data point has two features, and the Y values are just 1,000, and they are integer values. Okay. So these are a few samples from the data. Okay. Now these variables are NumPy variables. For you to be able to use them within PyTorch, you have to turn them into tensors. Okay. So here is a simple code to convert all the X as tensor. So touch dot from NumPy, you pass the value of X, and of course you have to turn it to float, okay, for numerical stability. So here I have turned all the X into a tensor and all the Y's into tensor. I can just view the first 5 data points, and obviously you can see they are now all tensor variables. Okay, remember at the beginning I said now for us to train a model to be able to identify this, we have to divide this into the parts we're going to use for training and the parts we're going to use for testing. So that's the train test, okay? And this line of code does that, okay? So we can borrow this function from the scikit-learn library, which is testing split, where we specify the x that we want to split and the corresponding y. And we specify the percentage of the test data, okay? If you recall, we are using a random seed of 32, which is similar to the random seed that we have here, okay? The idea behind this is just for reproducibility, so that even if you run it on your own device, you should be able to see the same result because we all have the same random seed, okay? So I split the data into tests and training, and this line essentially just looks at the number of training examples, the number of test examples, and their corresponding y labels. So now you can see we are saying that 800 samples will be used for training and 200 samples will be used for testing. So if you add those two, you recover the 1,000. All right. So to build a neural network in PyTorch, okay, you import the NN library. I think it stands for Neural Network Library. Okay. So here we just do a little bit of device check. We check whether we have a GPU running within the system. If we do, then we set the device to be CUDA. If we don't, then the device will be set to CPU. Okay, so at the moment, I don't have a GPU in my laptop, so what I get is CPU. Okay, so there are two ways to build a basic neural network in PyTorch. In fact, the most favorable way is to make a class. All right, so this is the class of neural network. Okay, there's one way to do it, where you make, you can call it anything you like. Here it's the circle model version 0. Okay, now the idea is you just make that class to extend the neural network module. Okay, and that's just it. Once you do this, then you are good to go. Okay, you can now set the variables within that class. For example, for this neural network, I want to multiply it with, I want to do a linear transformation. Okay, essentially that means I want to multiply whatever input that comes in, I want to multiply it with a linear layer, with a matrix. This matrix is going to be of dimension 5 by 2. Okay, so it's going to take 2 input features and it's going to bring out 5 intermediate features. Okay, this is my plan. And the next thing is I want to multiply that output to another matrix. So since this one is outputting 5, okay, I want that to be the input of the next multiplication. And at the end, I want to output 1. Okay, so this is like saying that I'm going to have an input for every input. Okay, I'm going to multiply it with a 5 by 2 matrix. Okay, after that, I also want to multiply that output with a 1 by 5 matrix. And you might be asking the question, why 2 exactly? If you remember, our input features are 2. Okay, so it's going to take an input feature, an input with 2 features, multiply it with a matrix of 5 by 2. Okay, meaning it's going to project that input into a 5-dimensional space, which is this guy here. And then we now multiply that also with another matrix of 5 by 1. So the final output is 1. And why is it 1? Because we want to do binary classification, okay, where the output can either be 0 or 1. Okay, so this is the setup. All right, so this is the setup for our version 0 model. And for the forward model, okay, so for the forward model, this is where the actual prediction goes in. Okay, this is actually where the prediction. So for every input that comes in, you first of all multiply it with the first layer, which is going to give you, multiply this input with a matrix of 5 by 2. Okay, whatever output comes out of this, you now pass it through the second layer, which now multiplies with the honor matrix of 5 by 1, okay, giving you final output. All right, so this is our version 1 setup. Now, an important thing here is there's no non-linearity in this. We're just multiplying with one matrix and another matrix. Okay, so everything is a linear. This entire setup is a linear transformation, just composed linear transformation. Okay, so as you can see, this is our circle model. It has two variables within, or you can call this. I don't want to use the word features because I'll be. It's going to be a clash of terminology. So let's just call it variables within this class. Okay, so there are two linear layers. The one is a 5 by 2 and the other one is a 1 by 5. Okay, so you might want to visually look at what is going on here. Okay, so for this, I'll move to this page. So let me post this link. You can also use this to visualize what is actually happening. So this is a tool for visualizing what we are doing. Just to give you an example, an idea. So that will be, so if you have your phones with you, you can check playground dot tensorflow, okay, .org. All right. So it is playground.tensorflow.org. So it's https:// the playground is small letter. Okay, if you follow that link, it will bring you here. Okay, all right, it will bring you here. Okay, now what we just did here is to set up a two layer neural network. So this is the first layer, this is the second layer. Okay, so let's try to replicate it here. All right, so this is the kind of data set we're using, this cycle data set. All right, now we have an input. It has two input features. What we are saying is that this output should be 5. So so we only have so the first one, the neuron should be 5. So there are 1, 2, 3, 4, 5. So this matrix here is a 5 by 2 matrix. Okay, so it multiplies this input, giving you 5 neurons here. Okay, and now we want a 5 by 1 matrix. So it means the last layer here, there should just be 1. Okay, so this is a 5 by 2, and this is also this is now a 1 by 5. So this is exactly what we just did here. Okay, all right, so there's no non-linearity. The activation is linear. Okay, now the reason why I'm showing this is I want you to try to understand what is happening. So whenever you hear the word linear, think of a straight line or a plane. Okay, so what we are trying to do is to find a plane that will separate this data. Okay, if you're able to draw a straight line that separates this data, okay, then this model, this our setup will work for these data points. Okay, but clearly these data points are more all circular. There's no straight line whatsoever that you can draw that will fit this line, and that's what we are going to see in a moment. Okay, so we have that. This is one way to set it up in PyTorch. Okay, another way to set it up in PyTorch is, so this is what I was just trying to explain, this setup here. This is exactly it. Okay, so you can do this interactively on your mobile phone. Okay, all right, another way to set this up is without, if you are not comfortable with the object-oriented style of defining this model, you can do something like this. Okay, you can do a neural network or sequential where you specify the 2 layers that you want the two linear layers that you care about, and you send it to touch. They are both the same. Okay. All right. So we have set up our network, this one. Okay, which is essentially this code here. Okay. We can test it. Remember, I told you guys that at the moment, these layers, these matrices are random. So if you make a prediction, it won't make any sense. Okay, it won't make any sense because now look at it. So right now, I just passed the test points. Okay, and my predictions are all untrained. So I check the length, I check the shape, and then I just look at the first 10 predictions. So these are the first 10 predictions. They don't look anywhere near what I really care about. Okay. What I want to see is values between 0 and 1. What I'm getting are even, in some cases, negative values. So it means my model is not really well defined for the task that I want. Okay. So you might want to go ahead and train this model. Okay. Remember at the beginning, I said to train a model, you need two things. Okay. You need the loss function, and you also need the optimizer. Okay. What is the purpose of the loss function? The loss function, the job of the loss function is to look at your prediction and the actual value, okay, and check the distance, all right, or measure the difference between those two, okay. If the values are high, it means you're not doing very well. So you might want to go and tune those weights because the only unknown that we have here are the weights of these matrices. Okay. And for you to tune those weights, okay, you need an algorithm to do that because these matrices are large. Okay. You need a more informative way to tune the weights. And this is where the optimizer comes in. Specifically under the hood, the optimizer works, okay, with different models. One of them is called the stochastic gradient descent. Okay. Don't want to bore you with the mathematics. Essentially, it's an iterative algorithm where that, at each step, it tunes the weights of the neural network. So the table you see here are different loss functions and their optimizer. For example, you have the stochastic gradient descent like I talked about. It is used for classification, regression, and many other problems. There's also another optimizer called Adam. Okay. All right. It is also used for classification, regression, many other problems. There's a binary cross entropy loss. This is now a loss function, and it is used specifically for binary classification. If what you want is a multi-classification task, then you will not use binary classification because this is only for two classes. Okay. For more than two classes, then you can use the cross entropy loss. Okay. You can also use the cross entropy loss on a binary problem because for two classes, it will fall back to being binary cross entropy. Okay. If you're doing regression task, you can define the mean absolute error, okay, which is also called the L1 loss. But be careful, this loss is non-differentiable. So don't want to go into that. You can also use the mean squared error loss. Okay, these are all specifically tailored for regression problems. Okay. So what you have here are just various ways of setting up or creating these loss functions. Okay. So if you've decided on the loss function you want to use to train a model, you define it. So in this case, this is binary cross entropy with logic. Okay. And we are using this. It is advised by PyTorch to use this because it's more numerically stable. Okay. So we define the loss, and then we define what the optimizer. In this case, we are using the stochastic gradient optimizer, where we are now going to pass the parameters, okay, of our model. And what are these parameters? The parameters are the weights, these two weights that we care about. Okay. So that's how we set it up. All right. Now, you might want to also evaluate the performance of your model once you've trained it. Okay. So a typical way, especially for a classification problem, you can just count the number of y values that you get correctly. Okay. That is known as the accuracy. function. All right. So here, what we do is we just count, okay, all the places where uh, the the one we know, which is a y true, okay, and what we are predicting, or we just count that. All right. That is, we sum the item, okay. All right. So that will give us a total number of all the ones we've got correctly, okay? And then we divide them by the average, okay? The average obviously is the length of either the predicts or the y true. Multiply by hundreds, so we get the percentage of the values that we're getting correctly. So that is what this function does. So we now have everything, okay? We now have how we can measure the accuracy of our prediction. We have how we can train the model. Okay. The next is to put the thing together in the training loop. So training the model is very simple. Okay. We make a prediction. All right. So before we do that, let's even see going from raw to predicted label. Fine. If you look at our design here, okay, our predicted label, okay, are in the range of negative some number to positive some number. Okay. We might want to restrict that. All right. Okay, so this is what we have here. So if you look closely, in do a test, you see that you have some values that are negative. Okay, because this model has not been trained, these values don't make sense. Okay, they are random. Okay, so you might want to get that after making a prediction, you might want to pass it through some function that will restrict the output to 0 and 1. And one of that functions is called the sigmoid. Okay, so once we've made a prediction, we call those ones logits. All right, and then we can now make pass it through a sigmoid function, which will give us a probability. So now probability values are between zeros and one. So we have these values. Mind you, we have not trained this model. These values are random. Okay, so you can do this thing the same. You can do the same thing in the visualization, where you'd say, well, at this point, okay, let's see, not regularization, activation. Okay, basically not here, so it's fine. Okay, so in the hood, I think this one does softmax for us. Okay, now as it stands right now, since we now have values between 0 and 1, okay, we can put a threshold. We can say all the values that are greater than 1, let's call it the class 1. All the values that are less than, sorry, all the values that are greater than or equal to 5, let's call it class 1. And all the values that are less than 5, let's call it class 0. Okay, we can do that. Okay, all right. So obviously you can see that we just basically round up the values. Okay, for other prediction, which are random for now, we test, we pass it through a sigmoid, and we round it off. Okay, and then we check for equality. Okay, so this is what we have. Okay, so if you do the y test, these are the values that you're having, which doesn't make any sense at the moment. Okay, we have not trained. Let's now look at how we are going to train this whole thing. Okay, this is exactly the same thing as if you go to the interactive window. Okay, so this is our model. Okay, this is our data set, which is a circle. We have two input features. Okay, we have one layer, two layer neural network. The first one has 5 neurons, so giving you a 5x2 matrix. The second one has 1 neuron, giving a 1x5 matrix. Okay, it's a linear activation. To train this on interactive tool, just hit the play button. It will start training. Okay, and we are going to do the same thing in the notebook. All right, so we start with the random seeds. Okay, we specify that we want 100 epoch. I don't know how many epoch we specified here. Okay, this has even gone over 100 already. But here we just trained that we want 100 epoch. Okay, and this is the training loop. All right, we loop through the number of epochs. Okay, we set the model to training mode, and now we'll make a prediction. Okay, so this is our data that we're using to train. We pass it through the model. Okay, we squeeze it to remove the extra dimensions, and then we pass that. We get our prediction. And what is our prediction? Our prediction is what we get when we pass the value into logic and then we round it off. Okay, so get either 0 or 1. All right. And then once we get our prediction, we check, are we really doing well? That is, what we got. Is this the same thing as our training? Okay. All right. If it is not, and we also calculate the accuracy. All right. So this is the idea. And once we do that, we zero out the gradient. Okay. Just think of it as a standard step, meaning you set all the previous gradients computed to be 0, and then you do back propagation. This will compute, okay? This will compute new gradients based on this loss, okay? And once we do that, we can now do a step. So this step involves tuning those weights that I talked about, okay? We can put it on evaluation mode and check the performance. So let's run this. Okay. As you can see, these are the inputs at different epochs. Okay. This is a test accuracy. We are getting about just 49%. Okay. On the training set after 90 epochs. And on the test set, we're only getting 53%. This is not good. Okay. This is like, it's still random. Okay. If you go back to the interactive window, you will see that this is the output. We are not doing well. It corresponds to the output that we get. This is even after we have trained it for like 1,300 and above. Let's even pause it here. Okay. So what is the problem behind this? Okay. Now the problem with this is this. Remember, this is a linear model. And what we are just trying to do is fit a straight line on the data. There is no way you can fit a straight line on this data. It is circular. Okay, so if you are to train this thing from now till infinity, you will never get a better improvement. So it means this model is ill specified. Okay, and that's why we are getting 53%. Okay, remember, this is a very, very important concept because you don't just, in real life, you don't just get data and just put stuff together and expect to get a good result. Okay, if the model is ill specified, then no matter what you do, your performance will not improve, which is what we are seeing here. Okay, because this model as it stands is only able to learn straight lines. Okay, all right. So this is that's that. So let's even see how this our model does when we evaluate it. So this is what I was saying. Okay, so these are our training data sets. Okay, this is our test data sets. And this is the line we're trying to fix. There's no way, there's no line that you're going to draw that will separate the blue from the red in this data set. It's not possible. Okay, this is the performance here on the test set as well. Okay, similarly to what you see here. It's not possible. So it means that this data, the data set obviously is nonlinear. Okay, linear, think of linear as straight line. Think of nonlinear as containing curves. So the trend of this data contains lots of curves. In this case, it is circular. So it's no way you can actually draw a straight line that will fit this. So we really need to go back to our model and change it. Okay. So this is the idea behind this. Okay. So improving the model, there are different ways to improve a model. You can add more layers. You can try it yourself on this interactive tool. Even if you add, let me add another layer. This is 3 layer now. Let's add, so this is now 3 layers here, 5 by 2, 5 by 5, and 2 by 5. Even if you train this, you will still not get a good improvement because everything is still linear. Okay, if you add a million layers here, you will still not be able to classify this problem. Okay, you're just saying you're going to use a lot of linear functions to try to predict this, which is not going to be possible. Okay, so in this our toy example, adding more layers will not solve the problem. Okay, you might say, okay, maybe I will train it for longer. Okay, in our notebook we only trained it for 100. in this interactive demo, it's already 625 and it's still not getting better. Okay. Now, we might want to change the activation function. Okay. At the moment, the activation function is linear, and this is where the trick, the magic comes in. Because we know that this data, the data set is non-linear. So if we introduce a non-linear activation function, then we're most likely going to do better. Okay. So that is the approach that we are going to take. Other approach involves maybe changing the learning rate, maybe defining a new loss function, or using something called transfer learning. All right. So here in the next cell, what we did here is to add a new layer, okay, and increase the number of neurons per layer. So here we say, okay, well, the first layer has 10 neurons as outputs. The second one is 10 by 10. The third one is 10 by 1. If you come here and check it out, so this is the first layer. If I increase it to 10, okay, I can't do more than 10 because of these two. So whatever it is, and I increase this one maybe to also 8. So this is 8 by 2, 8 by 8, and 1 by 8. If you train this also, you're still not going to do better, okay? Because these are all linear functions. You're not going to do better. There's no magic, okay? So this is what we have here, all right? So we increase the number of layers and see if we can actually do better, okay? Now, instead of 100, we change it to 1,000, okay? So this is after 1,000 epoch. We're only getting a test accuracy of 46%, training accuracy of 51%. It still doesn't make any sense. If you visualize it, you're still trying to fit a straight line. Okay? So what do we do? Like I said, this data is circular. It is not linear. Okay? So we need to introduce a non-linearity in our design. Okay? Non-linearity as a missing piece is the main problem for this issue. Even if you increase the number of layers to 1 million, you still will not be able to do better. Or if you add a single non-linearity, you will start making good change. Okay. So just to show that what we're actually doing can actually fit a straight line, we use a simple sample data set, which is actually a straight line in this case. Okay. So this is a simple data set. All right, not our data set now. Okay, so our testing points are the blue, okay, and our training points are the blue dots, and the testing points are the green dots. And then we use this same model, okay, all right, this same model that we just created, this last update. We used it on these very data sets. Okay, so we define that and the loss, and we try to train. Obviously, you can see that this does better, okay? So let's print it out. So you can see that we're able to get, this is our prediction, which looks like a straight line. It's getting very, very close to the actual data. Okay. Another way to look at this is if you go back to the interactive tool, let me even just change the data set. Look at this data set. Okay. Obviously, this data set is well separated, so I can fit a straight line here. Okay. I can fit a straight line on this one. With the same model, if I run this now, you can see that it perfectly separates the data, okay, into two classes, one on this class and one on this. But this is actually separate. You can actually draw a straight line around this. But in the case of the circle data sets, you cannot draw a straight line here, hence the reason why it cannot fit it. Okay. All right, so I think I have a few questions. Is there a way you can know if the data is linear before running it? Actually, if you have a 2D data set, that is, if you have just two features, you can just plot it. Okay. If you plot it, you do a scatter plot. For example, in this case now, this is 2D data set. So if I do a scatter plot, I can actually see the trend. That will tell me whether it is linear or not. If it's also 3D data set, you can plot it using a scatter plot, a 3D scatter plot. You see the trend, okay? But if it is beyond 3 features, there's nothing you can do, okay? So to answer your question, just assume that every data set that you see is nonlinear, okay? And treat it as a nonlinear data set, okay? In other words, you should introduce a nonlinear activation function. and you'll still do better. Okay, so what I mean by that is if you go back to this um, this separable data, and then you change it from being a linear, maybe to any of these nonlinear function, or explain in a moment. Let's say tan, okay, and then you run this, you still do better, okay, you still do better. So assuming that every data you see is nonlinear is going to help you, okay. But let's not jump the gun. Let's just continue. So the material is actually in the Telegram page. You can Telegram group. You can check it out there. All right. So now, it's like I said, the missing piece is the nonlinearity. Okay. So all we just need to do is add a nonlinear transformation to all those our matrix multiplication, and we'll do well. Remember, this is our data set. Okay. All right. We make it to tensor. Now we introduce nonlinearity. Specifically, the nonlinearity we are introducing here is a ReLU. Okay, we'll explain what a ReLU is in a moment. Okay, but what essentially it does is it takes the input, okay, and for certain values it sets to 0, and for other values you just leave them the way they are. Okay, so the model is still remaining the same: 2 inputs, 2 by 10, 10 by 10, and 10 by 1. But now we just have an additional addition, which is a ReLU. Okay, this captures the nonlinearity in the system. All right, so now we pass it through do the first multiplication, the second multiplication, the third multiplication, and then we pass it through a ReLU. Okay. Oh, sorry. We do the first multiplication, pass a ReLU through it. The second modification, pass a ReLU to it, and so on and so forth. Okay. So a ReLU does not have any weights. It's just a function. It's just a pointwise function. There's no weight to train. We'll see that in a moment. So let's create this model, okay, and set up our loss and do our training, okay. It's exactly the same thing as here. These are our data sets, okay. For each of the activations, we set up a ReLU, okay. All right. If you look closely in each of the neurons, this is now the visualization changes. Okay. All right. So now we have ReLU for each of the layers, and then we can run this. Okay. You see the difference? Okay. From the difference here, you see that we are now able to capture these, this nonlinearity that is inherent in the data. Okay, so if I run this also, you can see I'm already getting 79%. Now with this case, if I decide to now train it for longer, because I only trained it for 900 epochs, if I decide to now train it for longer, I'm most likely going to get better. Okay, because I now have a model that properly describes the trend in my data. Okay, so let's evaluate it and test it here, and this is what you see. Okay. All right. Like I said, if I train this for longer, let's just say 3,000. Okay. Now it's even 100%, 99%. So if we run this is it. Okay. Because the model is now properly specified, okay, I can now train it for longer and do better. Okay. Unlike the previous case where the model is not, the model is ill specified. Okay, I'm trying to use a linear model, to get a trend from a nonlinear data, and that's why I wasn't even doing very well in the process. So this is the idea. Okay, like I said, the rule of the thumb is always assume nonlinearity in the data. Okay, and you most likely get it right. Okay, so what are these nonlinear activation functions? What do they actually do? Okay, so let's just test them and see what they look like. So we generate just simple data from -10 to 10. Okay, if you plot that, you just have data from -10 to 10. This is like a straight line. Okay. Now, what happens if I pass this through a nonlinear function? Okay, like a ReLU. What is actually a ReLU? What does it do? Okay, a ReLU says, well, if any number is negative, set it to 0. Okay, all right. If it is positive, leave it as it is. So you expect the ReLU to squash from this point all the way to this point. You squash it to 0. Okay, and then from 0 and above, it will leave it the way they are. Okay, so this is the function. Is a maximum between 0 and x. So if you run it on A, which is our input, this input here. Let's plot it again. You see that all the numbers that are less than 10, in this case, are now 0. Okay, and all the numbers, so all the numbers that are less than 0 are now squashed to 0, and all the numbers greater are now left as they are. So you have this piecewise function, okay, that is non-differentiable at this point. Okay. Another type of nonlinear function is the sigmoid, okay? Well, people mostly use this to get out probabilities, okay? Because the sigmoid function will produce numbers between 0 and 1, okay? Now, a ReLU function will produce number between 0 and infinity, okay? Any numbers less than 0 will be 0, and any other number to infinity, okay? But the sigmoid is going to give you numbers between 0 and 1, all right? So if you run the sigmoid function on these are our inputs, you get numbers between 0 and 1. What is actually the sigmoid function? This is the definition, okay? It's defined as 1 all over 1 plus e to the negative the input at I, okay? And this is the implementation here, simple function, all right? So if you plot this now, what you get is the S shape, okay, from 0 to 1. And I think that is where the name comes from, sigmoid. So when you hear sigmoid, think of the S shape, okay, giving you values from 0 to 1. So this looks more like a probability distribution. Okay, so at the end, we can put everything together. In this case, we can use it to solve more complicated problems. Okay. So what we've covered, a bit. We recall in the case we said binary classification deals with 2 classes. All right. Multiple classification deals with classifying more than 2 classes. Okay. So let's now look at how we can, do multi-classification. In this case, we are going to use the make-bob dataset, which is also a synthetic dataset, just like the one you saw here. There. So here we specify the number of classes, and then we generate these samples. Okay. So these are the samples. All right. Okay. So in this case, you have how many classes? 1, 2, 3. There are 4 classes. So given any input, we want to identify whether the input belongs to the blue, the red, I think this is yellow, and whatever this color is. Okay, that's what we want to do now. All right, as before, we set up the device. Okay, now we set up the layer. Like I said, if you don't know whether your data is nonlinear, you just use nonlinear activation. Okay, it works for both linear data sets and nonlinear data sets. So here we set up 3-layer neural network. Okay, this one, and this one. Now, funny enough, in this case, we did not include any linearity. But let's even ask this question: is there a way we can draw it to straight lines on this data set? Is there a way we can draw different lines to separate these data sets, if it's possible? Okay. There's no way to get response, but the answer is yes. You can actually put a straight line here. You can actually put one here. Okay. You can actually put one here that will successfully separate this line. So let's see how it works. Okay, so we can say that in a way these data sets are linear in this space. But let's even see. Let's not jump the gun. So make that model, and we'll create the loss. Okay, in this case, the loss is now a cross entropy loss. We use stochastic gradient descent. All right, so this is just to test how the prediction looks like. You can see it doesn't make any sense at the beginning. And then, okay, and so this is just to test what we are seeing, the outputs, the prediction itself. And this is what I care about. This is the training, where we pass in the training inputs, okay? We pass it through a softmax. We'll make the loss, calculate the accuracy, zero out the gradients, calculate the new gradients, and make the updates. Okay. We're already getting 99%. Mind you, this is a linear model. There's no non-linearity here. Okay. Linear, linear, linear. And that's because this data can actually be separated by a straight line. Okay. All right, so let's evaluate it. Let's see. Okay. All right. So seeing this, like I said, we can actually feed a straight line. These are the lines. Okay. All right. So for this very data set, which is Bob data set, it is linearly separable. So a simple straight line without non-linearity can also do the work. And if you also introduce non-linearity, in fact, you can even do better because you might be able to trace out, these region. Okay. Well, that may not be so good because you might be overfitting. Okay. So that's that. There are a few exercises at the bottom here that I will advise you to try out. Okay. You can also, for this very make Bob data set, you can also try it. This is it here. Okay. Now, if you look at this problem, this is actually very, very interesting. Is there a way we can draw a straight line to separate this data? Okay. The answer is no, because if you put a straight line vertically here, okay, then, you'll be having two classes on one side. If you put a straight line here, you'll also be having two classes on one side. So if I do a linear model to do this, the results will be bad. Okay, let's try it. So let's say I have just linear activation, and I try to do the same thing here. It's not going to work. There's no straight line that can perfectly separate that data, even if you train it for a million years. Okay, but now this is where the trick comes in. Let me put a ReLU there and see how it goes. So all of a sudden, I'm perfectly able to classify or do this classification effectively just by introducing non-linearity. Okay, and then the cool part is if you look at each of these neurons, you'll see that these are the things that they have learned over time. Like, for example, this neuron is able to capture this type of vertical line. This neuron is able to capture these type of lines. This neuron is able to capture these, and so on and so forth. So what this neural network does is something called hierarchical feature learning, where at each layer, you're learning the orientation of the line, okay? And at the next layer, you can see you're learning something complex, which is a combination of these lines. So this one learns this region, this one learns this upper region, this one learns something like that, and so on and so forth. So this is why neural networks are really very powerful, okay? Because they're able to learn hierarchical features, okay? That naturally you will not be able to learn on a shallow network. So that's that for today. If you have any questions, you can post it in the Google Class, well, in the Telegram page, and also you can post any comment on YouTube. I'll find time to reply through Telegram. So thank you very much, and have a lovely day.